Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics and the chapters of mechanical actions and the equilibrium of a body. This exercise was a previous one on the Brevet exams in 2001, first session, third exercise. The title of this exercise is spring constant. In order to determine the force constant, spring constant K of a spring of negligible mass, we fix the extremity A of the spring and we connect to the free extremity a solid mass of mass m is equal to 20 grams. Then here, grams is not the SI unit of mass. In order to convert from grams to kilograms, we simply divide by 1000. Then 20 divided by 1000. Then this mass is given by 0.02 kilograms in the SI. Okay, see figure. So they mentioned the figure, now we can use it. The spring hangs vertically. So this is the spring. The point A, it corresponds to the point of contact between the between the string and the support, whereas B corresponds to the point of contact between the solid S and the spring. Now in number 1, they are telling me to name the forces acting on us. Tell for each of these forces whether it's a contact force or force acting from a distance. Now here, because the solid S has a mass, then it will be subjected to the weight, which is vertically downward. And because we have a spring, then it will be subjected to the tension force, which is along the string upward. Then the forces are given by the weight W and the tension T. Now in the same question, they are telling me to classify these forces to tell whether each force is a contact force or force acting from a distance. Then we know that the only three forces act from a distance are the weight, the electric, and the magnetic. Therefore, weight is classified as acting from a distance. And all other forces are classified as contact forces, in particular the tension force. Now in number 2, they are telling me the solid S being at equilibrium, S is in equilibrium. Then now we can use the condition of equilibrium. Take G is equal to 10 newtons per kilograms. Now part A, give the condition of equilibrium of S. Then how do you apply this condition? We always start by writing at equilibrium. Now, on the left hand side, we write the sum of forces acting on the solid S, and they are given by the weight and the tension. Therefore, weight vector plus tension vector. And on the other side, we write 0 vector corresponding for the condition of equilibrium. Now moving T to the right hand side, so the weight is equal to minus the tension vector. Now the first equation tells us that the effect of the forces acting on the solid S given by the weight vector and the tension T vector cancel each other to give us the 0 vector, whereas the second equation tells us that both forces have the same line of action. The minus sign is for the opposite direction and the equal is for the same magnitude. So this is the condition of equilibrium. Now in part B, they are telling me determine the magnitude of each of the forces acting on us. So we need to determine W and T, the magnitudes of the corresponding vectors. Now here, because we have the mass and we have a G, we can directly determine the magnitude of the weight, which is given by M multiplied by G. Now the value of M in the SI is given by 0.02 and the value of G in the SI is given by 10. Plugging this on the calculator, it will give me 0.2. Since everything in the SI, so the value of W will be in the SI, which is in newtons. Then the value of the weight is given by 0.2 in newtons. Now we need to determine the magnitude of the tension T vector. So here we don't know the force constant K and we don't know the elongation of the spring, therefore we cannot calculate the magnitude T using Hooke's law. However, here in part A, because we have determined the condition of equilibrium, then we have that the W vector is equal to minus T vector. And we can make use of this condition to say that in magnitude, So the magnitude of the weight is equal to the magnitude of the tension. And notice that here, because we are interested in the magnitude, so we drop down the vectors and we get rid of the minus sign. But we know that the value of the weight is given by 0.2 newtons. Then the value of the tension is given by 0.2 newtons. Now in part C, represent these forces on a diagram. So we need to represent the forces W and T on the diagram without using a scale, because here they didn't mention anything about the scale. So let's suppose that this is the solid S. This is the center of gravity G, and this is the point of contact B. So we know that the weight vector W acts at the point G, which is the center of gravity, because it's acting from a distance vertically downward. Then this is the vector W, which is worth 0.2 newtons. And now let's represent the tension T vector. Because it's a contact force, then it will act at the point of application, at the point of contact B between the two bodies, which is the spring and the solid S, vertically upward along the string. So this is the tension T vector, worth magnitude 0.2 newtons. Although here we represented the forces W and T without using a scale, but notice that I have represented W and T by the same length because they are equal in magnitude. So W here corresponds to 2 divisions and the tension T corresponds to 2 divisions. And this is because they have the same magnitude. Now in number 3, they are telling me the solid S is always in equilibrium, the elongation of the spring being 5 centimeter. So the elongation delta L of the spring is given by 5 centimeters. Knowing that centimeters is not the SI unit of length, in order to convert from centimeters to meter, we divide by 100. Then the elongation in this case is given by 5 divided by 100, which is equal to 0.05 meters. Calculate the force constant K of the spring, and this can be done by Hooke's law, because now we know the tension and the elongation is given. Then let's say apply Hooke's law. Hooke's law is given by T is equal to K multiplied by delta L, in which K represents the stiffness of the spring and delta L represents the elongation of the spring. Let me make some space. Knowing that here we are interested in calculating the value of K, constructing the triangle of this formula. Here, because we have multiplied and T will be at the top, K and delta L are at the bottom, putting our hand over K, then K will be given by the ratio T divided by delta L. The value of T that we already determined is given by 0.2. And the value of delta L is given by 0.05, everything in the SI. Plugging this fraction on the calculator, it will give me 4. Since both T and delta L are in the SI, so the value of K will be in the SI, which is in newtons per meter. Then the value of the stiffness of the spring, or the spring constant, is given by 4 newtons per meter. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.